Hello and welcome back to Physical Science Online. These are the BP3 notes for motion, Unit 1 in second semester. BP3 is a little bit longer BP. I'd say that the third BP is about, big picture, is about half of the total unit, whereas BP1 and 2 combined are about the other half. So this note session will be a little longer. I'm predicting it'll be at least 2 videos, aiming for 2 videos is what I'll say. But you might have to pause a few times and slow it down if you need to. So let's jump right in with where we left off. We left off talking about distance versus time graphs, just a reminder. Straight lines are constant velocities. And then curve lines, I know I can't do really good curve lines on a graph like this, but I kind of tried it from 7 to 10 seconds there, where it actually was changing velocities every single time. That is called an acceleration. Now in class, we talked about what really causes this change in velocity. If we're going from steep to shallow, like what happens there from 7 to 10 seconds, that means that we're slowing down. We're actually slowing down. We're not moving as fast in the negative direction anymore. If we'd go the other way, if we'd go from shallow to steep, we'd be going from not moving to moving faster, and all sorts of combinations there. So that's basically what's happening with acceleration, is you are changing your velocity. Let's see what that looks like. So acceleration is a change in velocity over a given period of time. Positive acceleration is thought of as speeding up. Not always, but usually. And negative acceleration is what we think of as slowing down. And this can be calculated. Just like velocity can be calculated, acceleration can be calculated. The acceleration equation, looks like the formatting didn't go perfectly, but it's off there to the left there. Acceleration equals delta v divided by delta t, where delta v stands for the change in velocity, delta t stands for the change in time, and a stands for the acceleration. 3 variable equations. You should be pretty familiar with these. It's just new variables to plug in, so you should be able to get through these pretty quickly. We'll do practice with them though. What can change acceleration? Well, if you're thinking about it, it can be a change in direction. So you can go from the positive direction to the negative direction. We're mostly doing 2-directional graphs. If you add in the third dimension, it gets even more complicated. But any change in direction is a acceleration. Positive change in speed, so speeding up. Negative change in speed, so slowing down. Or speeding up in the negative direction would also work. Or any combination of the above. Forces versus net force. So what causes acceleration, we talked about this in class a little bit, is forces. We think of like the force of gravity, why things accelerate as they fall towards Earth, why things accelerate as you hold down the gas pedal, stuff like that. It's all because a force is being applied. So what is a force? Force is a push or a pull on an object that ultimately can change its motion if it overcomes friction. Motion can be changed by either causing it to accelerate or by changing the object's direction, speed or direction. All a bunch of different ways of saying almost the same thing. Forces cause those changes in velocity, which is our definition of acceleration. So forces cause acceleration. All objects have some force acting on it. So there isn't a object that we know of in this universe that doesn't have some force acting on it. Think of yourself right now. You're sitting pretty still. We've had this discussion too. You're sitting there. You're not moving too much. Why? Why aren't you moving? Let's find out. Oh, I skip a slide. Newton's, a little out of order, but it's what's on the notes. I'm going to keep going with this video so I don't have to remake it. Newton is a new unit that we can use, a new chicken that we can use, abbreviated as N. So basically when you take mass and multiply it by meters per second, which is what a Newton is kilograms times meters per second. Gets really, really complicated. So instead of writing all that out every time, we honored Sir Isaac Newton and named it the Newton. So 1 Newton is equal to 1 kilogram meter per second. There we go. Now we're back to forces. I'm almost out of time, but I'm going to see if I can get through this slide yet. Forces are represented by arrows, which we label with newtons, and the arrows are pointed in the direction that the force is going. Then in the next video, I'll explain how we can use these force diagrams to explain motion. See you in the next video.